Okay, so let's look at this review problem for test 2. So the first problem on the test will be either moment about a point or moment about an axis. So here we have moment about a point. So what is the moment about point A? So for moment about a point, let's see, moment about A is equal to R cross F. So I need to find an R that goes from A to the force, and then I need to find that force in IJK form. So let me first find an R. Find an R that goes from A to the force F. So from A to the force F. R is a position vector. R is how far does it go? How far does it go in X? It goes, let's see, 250 plus 300. It goes positive 550 in the I. How far does it go in the J? So we're going from A to the force. So how far does it go in Y? 400 right here, plus 400 J. And how far does it go in K? It goes down this 200. So minus 200 K. That's the position vector. That does have units of millimeters. All right, so I've got my R. Now I need to look at my force F. Need to break it up into IJK form. So I see that's magnitude, and that looks like spherical angles. So how do I handle spherical angles? First break it up into Z and X, Y, then break it up into X and Y. So let me take that 100, and I think the first thing I'm going to do is take this 100 and find this fxy. Then I'm going to find the fz. So I know that fxy would be 100 cosine 30. So fxy 100 cosine 30. So that is 86.6. And fz would be 100 sine 30, but that's going down, and z is positive up, so fz would be negative 100 cosine 30, which is, 100 sine 30, which is negative 50. Alright, so that's, I have my z. Now I need to break this xy, this 86.6, break it up into x, let's see, x and y. So that 40 degrees right there would be for the y. So the fy would be 86.6 cosine 40, and the fx would be 86.6 sine 40, and both of those are in the positive direction, positive x direction, positive y direction. So this would be, fy would be 66.3, and fx 55.7. So here we have z, y, x. So I have all three components for this f right there. All right, so now I can do the cross product. All right, so let's do the cross product of r cross f. So the moment equals r cross f, and so r cross f would be the determinant of I, j, k of 550, 400, negative 200, that's the r, and then the f 55.7, 66.3, and negative 50. So let me do the cross part the way I like to do it. Take the I and then do this minus that, right? So let me do that. 400 times negative 50 minus negative 200 times 66.3, and that is my I component. Then negative the J component. So the J component would be 550 times negative 50 minus negative 200 times 55.7. So 550 times negative 50 minus negative 200 times 55.7. That's J. And then plus, and then the K component. 550 times 66.3 minus 400 times 55.7. That's the K component. So then let's do that math. And we would get that the moment about A. So I still have I, J, and K. Those don't go away. But the moment about A would be 33.27I minus 38.67J plus 14.2K. This does have units. It's a moment. Moment's force times distance. The forces were in newtons. The distances in millimeters. So Newton millimeters. And that is the answer for part 1. Okay, so let's go to the second problem here. So this one, so let this force be 30 pounds. So F is, 300 pounds. F is 300 pounds. Calculate the moment caused by the force about the BD axis. So moment about an axis. A moment about an axis. Moment about some axis. I know that the magnitude of the moment about an axis is equal to U dot R cross F. Alright, so moment about an axis is U dot R cross F. So the moment about the axis that I'm interested in, axis BD, so the U of axis BD is equal to the R that connects BD to F, and in this case F kind of goes from A to E, so F from A to E. So I kind of have 4 different options for my R. I could have the R go from B to A, B to E, D to A, and D to E. Anywhere on this BD axis to anywhere on the line of action of the force. So I think I'm going to choose B to E, right? BE, that's a pretty easy one. It's just, 35 in the J. So maybe let me go ahead and do that. The R that I'm going to choose is from B to E, and it is 35J units of feet. All right, so I've got that R. Let me go to the U. Let me find the U of the axis. The U of axis BD is equal to the R BD over the magnitude of R of BD. So so from B to D, this axis right here. I'm not really told the height from O to D, but using similar triangles, this base is 30, this height is 30, and so this base is 10, I'm told. So from similar triangles, the height is going to be 10. And then I do have this 10 foot right there. So RBD is how far does it go in the x direction? It goes back 10, right? It goes back that 10. Negative 10I. How far does it go in J? It doesn't. How far does it go in K? It goes up 10K. So that is my R divided by the magnitude of that. Square root. So then the U is negative 0.707I plus 0.707K. That does not have units. U is a unit vector. It's unitless. I took an R and divided by the R, so there are no units for that one. All right, so now I've got U of BD. Now I need the force in IJK form. So this 300-pound force, I need to write it in IJK form. And so that's dimensions, right? That's dimensions. So when I'm thinking dimensions, I'm thinking F equals FU, where U is R over R of AE. So this would be 300 pounds times the U of the force, the U of the line of action of the force. So that would be the R over R of the force. So the R from A to E. All right, the R from A to E. How far does it go in X? It goes 10. In the I, how far does it go in J? It goes 15. In the J, how far does it go in K? It goes down 30 in the K. It's a U, so I need to divide the R, divided by the magnitude of the R. 10 squared, 15 squared, 30 squared, square root. So this would be the F, written in IJK form. 85.8I plus 128.4J minus 257.4K. That's a force. I multiplied a force times a unitless unit vector, so it is still in pounds. All right, so I've got all three of those. I've got the U, I've got the R, I've got the F. Now I can do the cross product. I can do the math. So when it is U dot R cross F, I would do that all in one step and let me, instead of an IJK across the top, I'm going to put the U across the top. U comes first, right? It's U, then R, then F. So the U comes first. Negative 0.707I, 0J, 0.707K. Then the R. The R is just up here, 35J. So 0 in the I, 35 and 0. And then the F, the force, we do have an IJ and a K, 85.8, 128.4, and negative 257.4. So I'll do that cross product. So that would equal, let me go ahead and put that point, negative 0.707 times 35 times negative 257.4 minus 0 times something, and then negative, and I've got 0 right there, so I'm not going to bother writing the rest of that, and then plus 0.707, so I'm going to do that one, times that minus that, so times 0 minus 35 times 85.8. All right, and notice, remember, I don't have any i's, j's, or k's right there. I'm just finding a magnitude of the moment. So there are no i's, j's, and k's because right up here I've got my unit vector instead of I, j, k. I'll add those up together to just get one value, and I would get 4246 if I added all of these up. And so the units right there would be pound feet. So that is the magnitude of the moment about BD. That's the magnitude of the moment about BD. Let me go back up to the question, see if it asked for just the magnitude. No, it said calculate the moment, and it says express the moment as a Cartesian vector. That means in IJK form, so I need to express this in IJK form. I have the magnitude. How do I get the in IJK form? Just like F equals FU, M in IJK form is equal to M as a magnitude times U. M about the axis times U of the axis. So the moment about BD is equal to the magnitude, 4246, times U of BD, which I already found up here. The U about BD already up here, negative 0.707I plus 0.707K. So let me do that math. The moment about BD as a Cartesian vector is 4246 times 0.707, negative 0.707I plus 0.707K. So the moment about BD would be negative 3002 in the I plus 3002 in the K. It still has units. Units of pound feet, and that is the final answer. Okay, so this third problem is going to be like what the second problem on your test is going to be like, something to do with these reaction forces. There's also a distributed load right there. So let's look at this. All right, part A. Replace the distributed load with one or two resultant forces. So got to be ready for distributed load, got to be ready for uniform, triangular, one like this that goes from one height to another height. Don't forget the distributed load that is a function, and then you have to do the area under the curve, and you have to have that equation for the location of that. So go back and look at that before the test. So replace the distributed load with one or two resultant forces. Let's do that. So I'm going to break this distributed load up into a uniform rectangle and a triangle on top of that. So the rectangle, the uniform rectangular load, remember that you can replace a distributed load with that area. So the area of that rectangle, the area of a rectangle is base times height, base of 8 meters, height of 3 kilonewtons per meter. So we can replace that with 24 kilonewton force, and that's going to be at right at the middle, right, rectangular load just right at the middle at 4 meters from A. All right. Then the triangular load, the area of a triangle is 1/2 base times height. So that height of that triangle is it goes from 3 to 12. So that height would be 9 kilonewtons per meter. So this would be 36 kilonewtons. And where would that act? It would act at the centroid, or the center of that triangle, the center of a triangle is 1/3 closer to the taller, 1/3 closer to the taller side. So that would be really 2/3. So at 2/3 of 8 meters, what is that? That is 5.33 meters from A. All right, so I've sort of replaced those with, I'm going to leave them as with two forces, and then let me draw the free body diagram for bar A. So now I'm going to draw the free body diagram for bar A. So I have this bar. I have this bar. And I have a pin joint at A. So I have a pin at A. I'm going to draw that as AY and AX. Then let me take those distributed loads and replace those with forces. 24 kilonewton force 4 meters from A. So 24 kilonewtons right there, 4 meters from A, and a 36 kilonewton force, 5.33 meters from A. All right, and then I still have that 4 kilonewton force right here. So 4 kilonewtons, and I'm just going to go ahead and write 13 meters from A. And then over here, all right, that is a rocker. That's a rocker at B. So a rocker at B has one force, and it's perpendicular to the incline. So I have a force at B. I'm going to call it FB. It's perpendicular to the incline. The incline is 35 degrees from horizontal, so this force is going to be 35 degrees from vertical. Let me redo that. 35 degrees from vertical. All right, and I don't know it. I don't know AX, AY, or FB. And that's fine. I can solve for three unknowns. I have three equilibrium equations. All right, let me kind of make sure this is self-sufficient. If I ask for it, I want it to be self-sufficient. I am missing this 2 meter dimension right here. I have the angles, axes. Let's put your axes somewhere over here, X and Y. Very important to include your axes. All right, that is self-sufficient. All right, so all I have to do is, show that figure. And now I can write my equilibrium equations. So summing the forces in X. So what forces are acting in the X direction? AX, and then minus FB sine 35 equals 0. Summing the forces in Y. AY minus 24 kilonewtons minus 36 kilonewtons minus 4 kilonewtons, and then plus FB cosine 35 equals 0. And summing the moments, you might want to have started with this equation because it goes ahead and gives you an unknown. So summing the moments about A, AX and AY go straight through A. But then I have 24 kilonewtons acting 4 meters away, creating a negative moment. 36 acting 5.33 meters away, creating a negative moment. And 4 acting 13 meters away, creating a negative moment. And then the FB cosine 35, so this component right there, FB cosine 35, is acting 15 meters away, creating a positive moment. Set those equal to 0. Notice that the FB sine 35 would have gone straight through A. And let me just double check that to make sure it didn't give me any thickness or anything. Yeah, it's kind of acting right here. So this component would go straight through A. Also, it didn't give me any thickness or tell me anything about that, so I'm good there. So from this last equation, I would solve for FB. Undo. This last equation I would solve, and I would get FB is 27.7 kilonewtons, and it came out positive, which it should have because that can only be pushing. And then I would plug this back in right there to get AY. We got AY 41.3 kilonewtons, came out positive, so it means I drew it in the correct direction. And then plug that in up there, get AX is equal to 15.9 kilonewtons. All mine came out positive, so I didn't have to worry about it. But if your answer came out negative, it means you just drew it in the wrong direction. And on the test, if your answer comes out negative, I want you to make your answer positive and go back and redraw the arrow on your free body diagram. Don't erase it completely and redraw it, but just kind of mark through it and draw it in the correct direction, sort of show me that you started guessing that it was one direction, but your answer came out negative, so you went back and put it in the correct direction. But I'm looking for a magnitude, and then I'm going back and looking at your free body diagram to make sure it's written in the correct direction. This AY, I'm looking for 41.3, and I'm looking for it pointing up, and FB 27.7 pointed right there. And so that I have answered all the questions. I've replaced the distributed load, drew the free body diagram, and calculated the reaction forces at pin A and rocker B. Alright, so I am done for that one. Okay, so this is review problem number 4. Again, this is going to be kind of like problem number 2 on your test. The reaction forces, drawing free body diagrams, using those 3 equilibrium equations to solve for the unknown. So here, draw the free body diagram for bar AB and calculate the reaction forces and or moments at smooth collar A and smooth surface B. All right, so let me draw this free body diagram. So here, draw kind of the shape that I have. All right, and what forces are acting here? Well, definitely have this 100-pound force. I have this applied moment of 200 pound-feet. That's 3 feet from here, 3 feet from here, 2 feet from here. All right, now I'm going to start with this normal force at B. If I have an incline, just a contact surface, that is 12 by 5 by 13, I'm going to have a reaction force. I'm going to call this FB, and it's going to be perpendicular to the incline. The incline is 12 by 5 by 13, so this one would be 5 by 12 by 13. All right, it's perpendicular. Think when something's perpendicular, I kind of switch the x and the y axes, the x and the y dimensions. All right. Then over here at A we have a collar. And it's not a pinned collar, it's like a fixed collar. So that is definitely restricting the movement in this direction, right? So it's not restricting the movement along the collar, but it's restricting the movement perpendicular to that rod. So I have a force that is perpendicular. So I'm going to call this force A, and again, it's perpendicular to that rod, that 3, 4, 5. So this would be 4, 3, 5. But also, it is fixed connected to the collar. So it is restricting the rotation. If something is restricting the rotation, there is a reaction moment. So I'm going to draw a reaction moment, MA. So I'm just kind of guessing it is in the counterclockwise direction. So there's that reaction moment, MA. So let me include my axes. I'm calling to the right X. I'm calling up Y. And I think that is all. I think that is self-sufficient. It stands on its own. Now I don't have to go back and look at the figure anymore. I can just look at my free body diagram. Alright, and so once I've got that, I have 3 equations I can solve for 3 unknowns. My 3 unknowns, FA, MA, and FB. So, summing the forces in the x direction, I've got FA, the 4/5 component, is in the x direction, and then minus FB, in the x direction, the 5/13 component equals 0. Then summing the forces in y, I've got FA, the 3/5 component, so in the y direction, minus 100, and then plus FB, the 12/13 component, equals 0. And then summing the moments, I'm going to sum the moments about A. You could sum the moments about any point. Summing the moments about A, I need to include MA. I need to include that reaction force no matter what point I sum the moments about. Similarly, I need to include that 200. It's actually negative 200 right here. This applied moment, it is clockwise, and I'm saying counterclockwise is positive. All right, so summing the moments about A. FA goes straight through A, so don't have to worry about that. But I have this 100-pound force acting 3 feet away. Let me make sure everything's in pounds, feet, 200-pound feet. All right, so 100, 3 feet away, creating a negative moment. And then this FB, I'm going to need to break this up into its 2 components, and I think both of those components create a moment about A. So the FB, the 12/13 component right here, would be acting a perpendicular distance of 6 feet away, creating a positive moment. And then FB, the 5/13 component, that would be this component right here, it's acting a perpendicular distance of 2 feet away. That would be creating a negative moment, right? That would be creating a negative rotation, a clockwise rotation, and that would, so the moment arm would be 2. All right, so I've got all these set that equal to 0, and I don't have one equation that only has 1 unknowns, but up here I have 2 equations with 2 unknowns, so maybe write one in terms of the other. This top equation, I could write FA is equal to 0.475 FB, and then I could plug that in for FA right here, and then I could solve for FB. So I would get FB is 82.3 pounds, and FA I should get, so once I get that, plug this back in either up here or right here or right here, should get the same answer. I would get FA is 39.3 pounds, and then plugging both of those. Sorry, where did I mess up? Right here. All right, and then I can plug FB in down here to get MA, and so I would get MA is equal to 105 pound-feet. And in this case, all my answers did come out positive, meaning I have all of them in the right direction. But if your answer came out negative, remember, make it positive, go back and change your free body diagram. So that's what these three answers, and with the correct direction drawn on the free body diagram, that's what I'm looking for. Okay, and so here is review problem number 5. So remember, the last problem on your test will be a truss problem. You have to be ready for method of joints and method of sections. And this one says, well, first it says, determine the reaction forces. Determine the reaction forces at pin A and roller B. So I have to solve for those. Then, using the method of joints, determine the force in member CA. So this member that I'm looking for right here. It says state whether the force is in tension or compression. So, but remember, for a truss, the whole frame, the whole structure, the whole truss is in equilibrium, and then every joint is in equilibrium. So let me, especially since it asked for it, let me determine the reaction forces at pin A and roller B. I'm not going to redraw the whole free body diagram, but here at B, there is a force I'm going to call FB. It's at that 45-degree angle, and here at A, there's a pin. When you have the pin, you've got AX and AY. And so I can sum the forces in the X direction. AX minus FB cosine 45 is equal to 0. Summing the forces in Y. All right, I've got negative 50, negative 50, negative 50. And then I've got, the way I drew this, positive AY. And let's not forget about this positive FB sine 45, because this F has an F in the Y and an F in the X. Set that equal to 0. Still don't have one equation with one unknown, but if I sum the moments about A, then I could get that one equation, one unknown. So summing the moments about A, 50 newtons acting 6 meters away, creating a positive moment. 50 newtons acting 4 meters away, creating positive. 50 newtons acting 2 meters away, creating positive. And then I've got this FB, the FB, I think I'm calling this FB sine 45 and FB cosine 45. Sine 45 goes straight through it, but FB cosine 45 is acting 2 meters, this 2 meters away. Also, the way I drew it, also creating a, this one would create a, let's see here, would create a negative rotation if A is my pivot point. So this would actually be minus FB cosine 45 times 2 meters equals 0. Let me bring this up a little bit. So here I would get FB is 424.3 newtons. Then plug that in up here. AY is negative 150 newtons. So I want you to write AY is 150 newtons, and it is right here. It is not going up, it is going down. So, show me that originally, in this equation right here, you had guessed that it was going up, but it's actually going down. And then for AX, we would get AX is equal to positive 300 newtons. So I drew it the correct direction. All right, so that was part A. And a lot of times even if it didn't ask for those reaction forces, a lot of times you might need those or might want to go ahead and solve for those. All right, so now let's use the method of joints to determine the force in member CA. So now I'm going in and looking at the joints. The joints are in equilibrium. And I know at the joints, every force in every member is along the member. So maybe my first instinct is to go up here to joint A, but I would have 1, 2, 3 unknown, so I can't go there yet. Maybe I could go to joint C, but I would have 1, 2, 3, 4 unknown. So looks like I'm going to need to go to joint B and solve for those two unknowns. So let me look at joint B. All right, so I'm looking at joint B. And what do I have at joint B? I have that FB, that 424.3 at a 45-degree angle. And then I have, let's kind of go back up here, I've got force in AB going straight up. So force in AB going straight up, and the force in CB right there. All right, so now for every joint, you can sum the forces in X equals 0 and sum the forces in Y equals 0. So sum the forces in X equals 0. Actually, I'm not even going to do that. I'm going to sum the forces in Y equals FAB. And the way I drew it, FAB is going up. Right, I'm going to call X to the right, positive, Y up, positive. So FAB is going up, and 424.3 cosine 45 is going up, so that equals 0. So FAB is negative 300 newtons. So FAB is 300 newtons compression. All right, and just kind of looking ahead, that's once I solved for that, then I know the force in this member, then I can go to joint A and solve for the remaining two unknowns. So I'm just going to take that and jump to joint A. So now looking at joint A, now I solve for the force in AB is 300 newtons compression, so it is pushing 300 newtons. And so actually, kind of going back here, it is pushing, right? Compression is always pushing. Tension is always pulling. All right, so it is pushing 300. Let me kind of remember what I had back up here. AX and AY. I had AX and AY. This AY 150 down, AX 300 to the right. So AX was 300 newtons to the right, AY was 150 newtons down, and then I had the force in AF that was directly over, and the force in AC, which I'm looking for. And this one, I can look at the dimensions, but I can tell you it was 2 by 2, so it was at a 45-degree angle. All right, and so this one is what I'm looking for. This is what I'm trying to solve for. So looking at summing the forces in Y. Then FAF isn't even in that equation. Don't have to worry about that. Summing the forces in Y, negative 150, positive 300, minus FAC cosine 45 is equal to 0. So FAC came out to be positive 212.3 newtons. It came out positive. I guessed correctly. I guessed tension. So I need to specify it is 212.3 newtons in tension. All right. All right, so this last review problem is a truss problem, and it is a method of sections. So using the method of sections, determine the forces in members DC, let me see, DC right here, FC, and FA. All right, so kind of looking ahead, I'm going to cut it right here through those three members and look at one side or the other. This is actually the same truss as the other one. I could calculate the force in B right here and AX and AY if I need to, but looking here, I can just look at the left side of it. And I don't have any reaction forces, so that's what I'm going to do. I'm just going to look at the left side of it, and the ones that I cut through, I expose those forces. So let me kind of draw this E, F, D. I kind of like to draw it in as if it's just some solid object. What forces are acting on it? 50 newtons, 50 newtons. All right. Those are the only external forces. And then when I cut AF, I expose that force in AF. I'm guessing it's pulling. I'm guessing it's in tension. I expose the force in CF and the force in DC. All right. And so just, I'm not really grading this drawing, but for completeness, 2 meters right there, 2 meters from bottom to top, and this one is at a 2 by 2 angle, and my axes are X and Y. All right, I think that is pretty self-sufficient. So now I can do my 3 equilibrium equations for that section of the truss. So let's see. Summing the forces in the x direction, FDC plus FCF cosine 45 plus FAF is equal to 0. Summing the forces in the y direction, negative 50, and then minus FCF sine 45 equals 0. So from this one, I can get FCF is equal to negative 141.4 newtons. So FCF is 141.4 newtons in compression, right? Because I guessed it was in tension, but it is actually in compression. So it's actually in compression right there. Now, if I go backwards to an equation that I've already written, I'm going to need to plug in the negative number, the negative 141.4. But moving forward, I would just plug in any positive numbers because I know its direction now. So here, summing the moments, let me sum the moments about F. So summing the moments about F, FCF goes straight through it, FAF goes straight through it, this 50 goes straight through it also, but FDC, so FDC 2 meters away, creating a positive moment, and then 50 newtons right here, 50 newtons acting 2 meters away, the way I drew it, also creating a positive moment, equals 0. So FDC comes out to be negative 50 newtons. So FDC is 50 newtons in compression. And again, going back and plugging this back in, I need to plug in negative 50 right there. I need to plug in negative 141.4 right there to solve for FAF. And I would get FAF is equal to positive 150 newtons. So it's 150 newtons. I need to specify tension or compression. It is in tension. So that are the three forces that I was looking for. All right, so that hopefully will prepare you for the test. The first problem on moment about a point or moment about an axis. Second problem about reaction forces. A few things that I didn't show on that was a distributed load that is a function. Be sure you can do that. Also, be ready for any reaction forces, any collar, fixed support, pins, rollers, rockers, cables, links. Be ready for any of those and all of those. And also remember, for that problem, if your answer comes out negative, I want you to make it positive and go back and redraw it on your free body diagram. Make sure your free body diagrams are self-sufficient. Make sure you include all dimensions, angles. Make sure you draw your X and Y axes. Then for this last problem, it is either a moment about a truss or a moment about it is either a truss, a method of joints problem, or a method of sections problem, and I will tell you which method to use. You need to use that method. Generally, not a guarantee, but generally if we have a method of joints on this test, then on your final exam we'll have a method of sections, or vice versa. Make sure you can do both method of joints and method of sections. And then one last thing I didn't touch on this review is zero force members. Make sure you can identify pretty quickly zero force members. There are two ways, two things that could make something a zero force member. Two members that are forming a joint at some angle, or three members where two of them are along the same line of action. Then that third member that's coming off of that third member is a zero force member. So go back and review zero force members, and then I think hopefully that's enough. Hopefully you will be ready for the test. All right.